Alright, so in this video I want to take a look at some examples for triple integrals in spherical and cylindrical coordinates that we did not get to cover in class, beginning with example 5 right here. In example 5 you're asked to find the volume of the solid region bounded below by the upper nape of the cone, z squared equals x squared plus y squared, and above by the sphere, x squared plus y squared plus z squared equals 9. So, part of the trick of spherical and cylindrical coordinates is, generally speaking, your surfaces will give you your bounds for whichever variables you might be looking at. In this case, the sphere and cone are going to determine the bounds for rho and phi. So, x squared plus y squared plus z squared, we know that is rho, the distance from the origin. So, rho squared equals 9, which means rho equals 3. That describes this sphere. A little bit harder to do, but z squared equals x squared plus y squared. If you recall the conversions to spherical coordinates, this means that rho squared cosine squared phi is equal to rho squared sine squared phi times cosine squared theta plus rho squared sine squared phi sine squared theta, which I can factor out the common rho squared sine squared phi and then have times cosine squared theta plus sine squared theta. And this all looks like a big mess, but what this is telling me right here, since this is 1, this tells me that rho squared cosine squared phi is equal to rho squared sine squared phi, which would mean, since we know we're up here where phi is acute, this does mean that the cosine of phi is equal to the sine of phi, which implies that phi is pi over 4. And that's a long, detailed derivation. A quicker derivation, which might not be as easily accessible, if you think about polar or cylindrical coordinates, we know that z squared equals x squared plus y squared actually means that z squared is equal to r squared. Once again, since I know I'm above the xy plane, I know that z must be positive, so z would equal r. So if I think about what that means in 3 dimensions, that means I've got some radius right here, r, and I've got some height above the plane, z. What I've got here is a little right triangle with congruent legs, which of course, if the legs are congruent in a right triangle, that means I would have a 45-degree angle here, or for that matter, out here. So that's an arguably easier way to show that phi is in fact pi over 4. That's what will determine this cone. So then, what I need to think about is, how should I set this up? So I'm finding volume, which I know means I would put 1 in my integrand. But also, since I am doing spherical coordinates, I have to remember that extra factor of rho squared sine phi, and then I will have d rho, d theta, d phi. So these surfaces determine my bounds. The bounds for rho will be from 0 to 3. The bounds for theta, well, I make a full circle right here, so theta bounds are 0 to 2 pi. And the bounds for phi, well, I'm going from 0, that being right along the z-axis, the positive z-axis, down to pi over 4, hitting the cone. Now, since I can split this up into functions separately of rho, theta, and phi, I can actually split this into a product of 3 integrals. First off, my phi integral. Sorry, my brain worked a little bit ahead there. My theta integral, there's no theta inside, so I will have 0 to 2 pi of d theta. And my rho integral, I'll be integrating rho squared from 0 to 3. So if I do integrate these things, right here I will have, let's see, this is negative cos phi from 0 to pi over 4. times theta from 0 to 2 pi times rho cubed over 3 from 0 to 3. So if I evaluate these things, what do I get? Well, these two are a little bit easier to evaluate. This will give me 2 pi. Right here, this will give me 27 over 3 minus 0, so that's 9. So I've got 2 pi, I've got 9, and right up here, the negative cosine of pi, if I evaluate at pi over 4, I will have negative root 2 over 2, minus the negative of cosine of 0, so minus negative 1. So in other words, that is 18 pi times, I can rearrange this and call this 1 minus root 2 over 2, or any of a variety of equivalent answers. And you can approximate this with a calculator with something like that. This will come out to about 16.563. But the key here in understanding this, we need to know how to set it up. Again, we have this extra factor because of the spherical coordinate conversion. And like I said, a big part of this is understanding where I get rho, where I get phi bounds from. I want to evaluate the triple integral in this next problem of x, y, z, where E lies between the spheres rho equals 2 and rho equals 4, and above the cone rho equals pi over 3. So, it's a little bit hard to draw this out, but since I am above the cone rho equals 3, means I've got some cone right in here. I'm going between these two spheres, so while it can be a little bit hard to draw, maybe a bit hard to visualize, pretty obviously that gives us our rho bounds. So then what we would have here is triple integral x, y, z. So if I do my conversions there, x is rho sine phi cos theta, y is rho sine phi sine theta, z is rho cos phi. I'm running out of room because I've written too large. I don't want to forget my additional factor, rho squared sine phi, and then I need d rho, d theta, d phi. So my rho bounds, rho goes from 2 to 4. My theta bounds, well, again, between these two spheres above the cone, that means that's implying I'm making a full circle, so theta goes from 0 to 2 pi. My phi bounds, phi will go from 0 to pi over 3, again, because I'm going from the positive z-axis down to this cone. So, I can go ahead and clean all this up, and what's more, I can actually separate this, as I did the last problem, into a rho integral, a theta integral, and a phi integral. So if I do that, my rho integral, it looks like I'll have rho, 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 rho squared, so that's rho to the 5th, d rho. My rho bounds were 2 to 4. My theta integral, I have cos theta, I have sine theta. And then for phi, it looks like I have sine cubed phi, and then I'll have that 1 cosine of phi in there as well, d phi. Now, of course, you can evaluate this with a calculator. These can also be evaluated not too hard, without too much difficulty using U substitution. If you do use U substitution, you'll see right here, and this should make sense, this is coming from sine to the 4th of phi because that's the derivative of sine. And similarly, sine theta cos theta is 1/2 the derivative of sine squared theta. So if you did that U substitution, if you did just that bit of work, it would make sense that if you did evaluate this using technology or going by hand, this right here is going to give me 0 because I'll have 1/2 of 0 minus 1/2 of 0 because the sine is 0 at both 2 pi and 0. So this entire integral is just 0. All right, so another big part of this is not just understanding how to set up the integrals and certainly how to evaluate them. We want to be able to convert between rectangular, cylindrical, and spherical coordinates depending on what's most convenient, depending on what works. So if I want to change to cylindrical coordinates up here, I want to change from 0, 1 these are my bounds for y, these are my bounds for x, these are my bounds for z. So if I figure this out, this means that z is going between x squared plus y squared and the square root of x squared plus y squared. Now if I think about that, z equals x squared plus y squared, that's a paraboloid. And right here, if I think about this right here, z squared would equal x squared plus y squared, which is a cone. So I'm thinking about I have this paraboloid, and then inside that paraboloid I have a cone coming down like this. So I'll be integrating over this space in between the two of them. Okay. X is then going from 0 to the square root of 1 minus y squared, which that would mean that x squared is 1 minus y squared, so the region that I would have in the plane, also knowing that y goes from 0 to 1, let's see, so x goes from 0 to the top half of the circle. All right, let's draw this circle. So x goes from 0 to the circle, y goes from 0 to 1. The trace in the xy plane is this little quarter circle right here. That's the region I am integrating over. Visualizing this is really key to being able to actually execute the change in coordinates that we need to do right here. So if I am changing in coordinates, I need to think about, okay, cylindrical coordinates. So z will still be z, but I need to think about r and theta. So xyz. xy is r cos theta times r sine theta. Then I will have z, and then I know I will have r dz dr d theta. My z bounds here, I'm going between these two things. So again, x squared plus y squared is r squared. The square root of r squared is just r. And based on, again, using these two together to figure out this trace, I can see that the bounds for r should be 0 to 1. And the bounds for theta should be 0 to pi over 2. So, this is the conversion. Probably a more practical answer would be to simplify this integrand, which appears to be r cubed z cos theta sine theta. And then again, if you did actually need to integrate that, because the bounds of z are determined by r, you would need to evaluate the inner integral first. But once you had that, you would be able to use that splitting up property that we've been using so much. Let's change to spherical coordinates. Here, I have all of these things. So, in this one I tried to build it from the surfaces down. What if we tried the opposite order? What if we thought about what each of these things are? So, my bounds for x and y, right in there. So y is going from 0 to 3, and x is going from 0 to the square root of 9 minus y squared, which means, again, if I squared that, x squared equals 9 minus y squared. That's a circle of radius 3. X is going from 0 to the circle, y is going from 0 to 3, so again, my region in the xy plane is a quarter circle. What about these functions right here? And again, I'm asked to change to spherical coordinates. Let's focus on these equations. So if I think about z equals the square root of 18 minus x squared minus y squared, and z equals the square root of x squared plus y squared. So we did an example like this already. This would mean that z equals r, which the reason that helps us with spherical coordinates is because we know this is describing a cone where phi is pi over 4. Right here, if I square z and square this, I will get z squared is equal to 18 minus x squared minus y squared. I can rearrange that a bit and say x squared plus y squared plus z squared equals 18. In other words, rho squared is equal to 18, or rho is the square root of 18, which we could rewrite as 3 square root 2. So, let's think about this. What will our triple integral be? So inside I have x squared plus y squared plus z squared. That is what rho squared is defined to be. I know I will have that additional conversion, rho squared sine phi. d rho, d theta, d phi. My rho bounds, well, what's going to be happening here is I'm going between two surfaces. What am I going between? I'm going between a sphere, is what we discovered this was. This is a sphere of radius square root of 18, and this was a cone forming a particular angle with the positive z-axis. So rho then is going from 0 to the square root of 18, or 3 square root 2. Theta, well, taking a look at this diagram right here, I can see that theta will be from 0 to pi over 2. And phi will go from 0 to pi over 4. So, I've converted it. Again, simpler, what you would probably see is rho to the 4th sine phi as your integrand. And you would have to understand that what you're actually integrating then, the integrand is rho squared, and this came from that conversion. An interesting thing about this is we did some problems like this before, where if I do draw these things, Again, x squared plus y squared plus z squared equals 18, so let's try and sketch a sphere as best we can. As best we can, and that's not a particularly good sphere. So I got a hemisphere there, and then we know this is a cone, so I'll have the cone meeting the sphere in some angle. Interestingly enough, what's happened here is, in previous examples we saw right here, you might be given the equation of the cone, which is z squared equals x squared plus y squared, and the equation of the sphere, and what you would need to do is figure out this curve of intersection between the two of them. Since you have been set up with the triple integral, that's really already been found. So if you did use these two things together, you would find that the curve of intersection is a circle of a radius 3. Alright, let's do one more example, converting to both cylindrical and spherical coordinates. Alright. So if we do this, and again, we want to think about the trace, we want to think about what these surfaces are, that will really help. So I can see that x goes from 0 to 1, y goes from 0 to the square root of 1 minus x squared. So y equals the square root of 1 minus x squared, that's the top half of a circle of radius 1. X is going from 0 to 1. So again, I know right here I'm integrating over a quarter circle. This is very common if you're converting to cylindrical or spherical coordinates. Ideally, you want to be integrating over some kind of circular region in the xy plane, because that will give you simpler values for r and theta, and then in turn, when you use spherical coordinates, phi and rho as well, really. But again, this right here is y equals the square root of 1 minus x squared. The surfaces I'm going between are z equals 0 and z equals the square root of 1 minus x squared minus y squared. Again, I can square both sides. Z squared will equal the radicand right here, and rearrange a bit and get x squared plus y squared plus z squared is equal to 1. So it really does help to be able to visualize these things. If I do visualize this, then I know what I'm doing is I have here now a sphere of radius 1. And I'm drawing it a bit more like a parabolic shape, which is my mistake. It is a sphere. So, we're integrating over a sphere. This is our integrand. If I put this into cylindrical coordinates, what would I have? Well, in cylindrical coordinates, the square root of x squared plus y squared plus z squared, well, x squared plus y squared is r squared. So I would have the square root of r squared plus z squared, which of course can't be simplified, times r dz dr d theta. My z bounds, well, I'm going between the sphere and the plane. So z goes from 0 up to this sphere, which is the square root of 1 minus x squared minus y squared, or rather 1 minus r squared if I'm in cylindrical coordinates. I can figure out my r bounds using this trace pretty easily. r goes from 0 to 1. Theta goes from 0 to pi over 2. What would this same integral look like in spherical coordinates? So, x squared plus y squared plus z squared, all of that is rho squared. Square rooting rho squared would of course give me rho, and then I have that additional conversion factor, rho squared sine phi, d rho, d theta, d phi. All of this, mind you, both of these things right here, those are dv. Okay. This is a necessary part, just as the r was for polar and then cylindrical coordinates, necessary conversion. So what will my bounds be for rho? Well, I'm going from 0 out to the sphere, so rho goes from 0 to 1. Theta, well, again, based on the trace that's described, I know that theta goes from 0 to pi over 2. And phi will go from 0 at the positive z-axis down to, well, if I'm going down to the plane, z equals 0, z equals 0 would mean that phi is equal to pi over 2 because I'm going 90 degrees from the positive z-axis. So these are all equivalent integrals. Any of them would give me the correct answer. And what you can see, obviously, the real utility of converting these things is this integral up here is somewhat nasty. This is a bit simpler, but conversion to spherical coordinates, not surprisingly since we are integrating over the volume of a sphere, spherical coordinates will give us a much simpler integral.